So these are, you can think of it as the, microscopic friction, sort of, So you roll the ball, and the ball is rolling just because you have microscopic friction. So this is the biological friction, in a sense. You have two pairs that interact, and it creates this, rolling phenomenon. Okay. So now the whole purpose of blood and blood cells is to fight infection. So for instance, I have a damage in my tissue. I made a wound. For instance, this is one of the, so there's a damage here, and then platelets are moving to, to the site of the damage or tissue injury, and then, in order to make a plug. And these guys are supposed to find this damage, bacterial infection or viral infection, and supposed to come and start healing it. Okay? So that's the biological function of blood cells. I mean, blood cells are immune system cells. This is our immune system. Okay, so leukocytes are cells of the immune system. They're supposed to fight infection, I mean, I don't know, any infection, swine flu, okay, any infection. So, okay, so that's the prehistory. That's the, this is the biological function of leukocytes, and these are the observed phenomena. And nobody can understand why they have shear threshold, okay? So shear threshold, for instance, if I'm looking at this graph, so I have shear stress. You saw dynes per squared centimeters in that movie, remember? So if I plot velocity, or I plot tether frequency, or I plot anything else, what I'll have biphasic behavior. Something goes up and then goes down. Nothing monotonic. So one would expect monotonic increase with the shear stress of the average velocity, okay? Monotonic decrease of the average waiting time, okay? Monotonic decrease of the average tether numbers, etc. But what they observe first increase and then decrease. So this phenomenon is called shear threshold. So there should be a threshold. For instance, for this particular graph, or for this, you have this x value that corresponds to the maximum, in the y-axis. Okay, this is called shear threshold. And the shear threshold effect, if you read off from the papers, the average number of following leukocytes, velocity, tether frequency, and the average waiting times first increase and then decrease with shear stress or shear rate, okay, of the blood flow. So now people got curious. They wanted to know why there's such a thing as shear threshold effect. And luckily, with the advent of single molecule spectroscopy, which allows, for instance, this is a typical setup for AFM-based dynamic force measurement, okay? And this particular experimental setup allows us to probe the strength of protein-protein interaction at the single molecule pair level. So there are just two molecules here. One is a receptor. This is P-selectin, okay? And this is PSGL1, the ligand. So this is the pair of biological molecules that exist, that are the most relevant, okay? We have, this is expressed on the endothelium, and these counter receptors are expressed on the membranes of rolling leukocytes, rolling neutrophils, et cetera, et cetera, et cetera. So the way this experiment is done is okay, the way it's done is the ligand is being attached to the cantilever tip, and so this is a linker, short linker, it's shown in red, and then the protein of interest, for instance, in our case, is P-selectin receptor, is attached to the surface, and then what cantilever tip does, it brings the ligand close to the receptor to allow for the bond formation, and some of the time, this event is not happening, right? So this is nothing. So you brought it to the contact, you made a contact, but they did not interact, so there is no force signal. But sometimes the binding is successful, and then once you bind, cantilever tip immediately goes up. The force is being applied to the bond, and then if there's successful binding, then there will be a force increase, and then once you have rupture event, then the force is going to drop. And then you do it many, many times, so you have thousands and thousands of these events. Some of them are successful, some of them are not successful, but then you have these force peaks, and then from that you can obtain histograms of rupture forces. So for instance, this is a histogram of rupture forces. Another way of doing it is you apply constant force. So there's AFM, similar AFM experiment, but more sophisticated because you have some sort of a feedback, and you apply constant force, and then you look at the distribution of lifetimes. If that's the case, if you have that mode of experiment, then you study the distribution of lifetimes. So there are two types of observation. One is lifetimes, and then you study the distribution of lifetimes, and this is the experimental distribution of lifetimes, histogram of lifetimes. Or your experimentally measurable quantity is force, rupture force. Then you collect those, then you construct, then you analyze the distribution of rupture forces. So there are two types of theory here, okay? But this is your experiment, okay? So now what people have done, they just, people who were interested in figuring out why they have shear threshold effect is that they just isolated this pair of interacting molecules because they knew that there were other experiments supporting this. So they figured out that something is strange going on between this two couple, and then they started to do single molecule experiments just on these molecules to figure out the molecular origin of shear threshold effect. Okay, that's what they have done. And yes.
Explain the histograms of the panel, and what is the horizontal axis?
Horizontal axis, this is lifetime. I apply force and then I wait. 1 second, 2, 3. 3, 5, ruptured. That's my first observation. Then I do the same thing. It ruptured in 4.7 seconds. Then I do the third measurement. It ruptured in 1 second. So I collect all these rupture times. We call them lifetimes. Lifetime of the bond lifetime. We lump them together, and then we make a histogram. So this is an example of a histogram of the lifetimes.
The relation between this histogram, the lifetimes and the upper panel of the time evolution of the force is
Right.
Decay.
Yeah.
That's decay rate.
No.
The decay time.
If I do this at time-dependent force, okay, what I can do is I can linearly increase force from 0. When I do this, then after that I linearly increase force with time. If I do that experiment, then this will be my observation. And then I'll be doing this. I'll be analyzing distribution of rupture forces. Okay? I can also perform another experiment. It's not shown in here, but I can perform another experiment where I don't create force starting from 0, but initially, once I bind, there's a feedback mechanism that allows me to apply constant force. So, change it to a constant value such that there'll be always a constant. It's like constant perturbation or time-dependent perturbation. That's the difference. There are two types of experiments. So if you're doing constant perturbation experiment, then these are the quantities. You're analyzing lifetimes. If you're doing time-dependent perturbation, and then you have time-dependent force, then you look at the rupture forces. And, they are somewhat related, but it's same as to say non-equilibrium statistical mechanics, and let's say, this is non-equilibrium, and this is near equilibrium kind of experiment, something like that. Okay.
So you need two types of.
No, you can do just one. You can do just one, and different people are doing different types of experiment. This is more difficult because you have to have a feedback. If you have a feedback, then you have noise. Then you have to do more measurements in order to reduce noise, in order to obtain higher statistical significance. Whereas this one is more straightforward. No feedback is needed. It's easier, but then the perturbation is time dependent. Then it's difficult to write theory. It's difficult to interpret the results because you have time-dependent perturbation. It's easy to work with time-independent perturbation, right? So this is difficult, easy to perform, but difficult to interpret. This one is very difficult to perform, but easy to interpret.